All right, so here's where the fun begins. Balancing redox reactions. Now, here's what's tricky about this. They give us an example here of a net ionic equation. This has all the spectator ions removed. So it looks like we've got some cerium, we've got some tin. This is going to be awesome. People might look at this and say, hey, it's balanced. There's one atom of everything on both sides. It's a balanced equation. Not so fast. When balancing a redox reaction, not only do we have to balance the atoms, so we have to have the same amount of atoms of all elements, but we also need to make sure that the electron transfer is equal. If one side of the reaction is going to donate 2 electrons, the other side has to pick up 2. Oxidation involves losing electrons. Reduction involves gaining. They go hand in hand. So often we have what we call a half reaction. One half of this reaction is going to be the electron donation. The other half is where we pick up the electrons. And not only do I have to make sure that the atoms balance, but I also have to make sure that the electron transfer balances. If, one side needs 3 electrons, but the other side only donates 1, this thing's not going to work. That's not a balanced redox reaction. So you have to be a little careful. If they say something about balancing and oxidation reduction, you have to use what's called the half reaction method. And this is something that they'll do in a multiple choice question, and they'll try to trick you, and you'll go through it too quick and you'll say, oh, it's balanced, all the atoms are balanced. But if they indicate in any way that this is a redox reaction, you must identify the electron transfer and make sure that that is also equal. So the first thing we're going to look at is how to split this into the 2 half reactions, the oxidation half and the reduction half. First thing I would need to do is assign oxidation numbers, but that's actually done for me. In this case, everything is scaled down to like a net ionic. And so we kind of say, like if it's metal ions, the charge is the oxidation number. So I don't have to worry about any oxidation rules or anything like that. Those little charges are the oxidation numbers. Oxidation, oil, involves losing electrons. If you lose electrons, your charge becomes more positive. That's tin. So the oxidation half reaction gets written like this. 10 plus 2. There we go. Or you could say 2 plus goes to 10, 4 plus, or plus 4. Which probably means that the cerium is the reduction. Reduction involves gaining electrons. If you gain electrons, you're becoming more negative, or in this case, less positive, I guess. So we'd say it's the cerium plus 4 going to cerium plus 3. So that's always the first step. We want to split these into the half reactions. We want to identify the oxidation half and the reduction half. From there, the fun begins. All right, so let's look at one of my favorites. Here's a whole bunch of rules, and we'll get to that. They're all kind of listed in this first example. We're going to be doing a reaction very similar to this in the lab. Permanganate, MnO4-1, is reacting with some iron plus 2. Now again, this is scaled down to net ionic. In the lab, we're going to use some potassium permanganate, but the potassium is a spectator ion, so it's not listed in this equation. We want to get the 2 half reactions first, so I like to identify the oxidation numbers right away. Now, a lot of these are just ions, so the charge is the oxidation number. The only thing I need to look at is that permanganate ion. Oxygen is always -2. There are 4 of them, which gives me a -8. The permanganate ion needs to be left with a -1 charge, leaving manganese as a +7. Whoa, that's crazy. Everything else is the charge. Iron plus 2, iron plus 3, manganese plus 2. So we write the two half reactions. Oxidation involves losing electrons. If you lose electrons, your charge is becoming more positive. I see it. Iron. So we'll just kind of mention that this is the oxidation half reaction. Iron plus 2 going to iron plus 3. Oxidation involves losing electrons. All right, so that leaves reduction. Reduction involves gaining electrons where the charge will become more negative, less positive. It must be the manganese. But now when we write this, if that manganese is part of a compound or part of a polyatomic, we're going to include that whole species. So we'll list the permanganate ion going to manganese plus 2. Cool. Okay, so here are my two half reactions. Now, honestly, you can usually kind of pick out the half reactions pretty easily. Obviously, the two iron are going to go together, and the two manganese particles are going to go together. Now, you might have to look at the oxidation numbers to decide which half is oxidation and which half is reduction. Okay, so I got them split. First thing you do is balance all the elements besides hydrogen and oxygen. And guess what? That is already done. And we kind of treat these as two separate equations until we get to the very end. But in both cases, I have one iron, one manganese, one manganese. This is done already. So we'll just transfer these. Plus 2 going to manganese plus 3. And then I've got the permanganate turning into the manganese plus 2. So they do kind of walk us through this step by step. They're holding our hands as we go through this first equation, which, again, I'm really having fun. Next step, balance the oxygen by adding water. Now, these are usually in some kind of solution. I've got these aqueous ions, which means that water is present. If you don't have any oxygen, you don't have to worry about it. So in this iron, it is what it is. Plus 2 going to iron plus 3. But I will have to deal with that in this permanganate one. Okay, so let's see what we got here. We're going to need to balance the oxygen. I have one manganese on each side, but I don't have any oxygen on the product side. But there would be water present in the solution. So we'll go permanganate going to manganese plus 2, and we'll add 4 waters. We'll add 4 waters to balance the 4 oxygens. All right, now they may mention this, usually they do, that these reactions often occur in an acidic solution. Usually they'll list that. They'll say, balance this reaction as it occurs in acidic solution. That's what's going to happen in the lab. We're going to have to add a little bit of sulfuric acid, which means that hydrogen is present. Acids contain hydrogen. So now we just added water, which balances out the oxygen, but it also adds hydrogen. So we balance the hydrogen by adding just hydrogen plus 1 ions from it being an acidic solution. So I'm going to need to add 8 hydrogen ions to my permanganate, Mn plus 2, and the 4 waters. You are all set. I don't have to worry about that with my iron half. I'm kind of liking that. I have no oxygen. I have no hydrogen. It is what it is. Okay, so we balanced all the atoms besides hydrogen and oxygen. Next we add water. That'll balance the oxygen. Then we add hydrogen plus 1 ions to balance the hydrogen by adding water, and since it's an acidic solution, there would be hydrogen present. Next order of business, the charge. And again, this is kind of where people will go wrong. They'll try to just go right ahead and balance this equation. And then they'll get kind of stuck. If you look at this original equation, they'll say, well, where's the oxygen go? That doesn't make sense. Yeah, you can't just attack these like you're balancing an equation in physical science. You have to use this half-reaction method. It's the only way that you're going to get all the atoms to balance, the charge to balance, and now we'll see, where did that oxygen go? Oh, yeah, it's in water. We had to add water to balance the oxygen. Okay, so we finally get to play with this iron. When we talked about balancing the charge, our only option is to add electrons. So in this case, I need the charge to be the same on both sides. All I can do is add electrons. So I'm going to have to add an electron to the product side. Now both sides should have a charge of +2. Interesting. And now this actually makes some good sense, because originally I listed this as the oxidation half. Oxidation involves losing electrons, so I should have an electron produced. Reduction involves gaining electrons. So if I look at this manganese half reaction, the reactant side has a total charge of +7. I've got the 8 hydrogen, those are each +1. The -1 on the permanganate leaves me a +7. On the product side, I have a +2. The only thing I can do to balance the charge is add electrons. So to get the charge the same on both sides, we're going to have to add 5 electrons. Then each side should have a charge of +2. Everything else stays. Permanganate. And we're going to form the manganese +2 and the 4 waters. Awesome. Okay, so now this makes sense. We had the oxidation, the iron half, losing the electrons. The permanganate, the manganese side, is the reduction half reaction. We're gaining the electrons. The only problem is that the electron transfer needs to be the same, and it's not. Right now, my reduction half needs 5 electrons. My oxidation half is only producing 1. So before we can add these half reactions together, we have to make sure the electron transfer is the same, and if it's not, we'll have to multiply 1 half or maybe both half reactions so that the number of electrons transferred is the same. In this case, all I have to do is take this iron half and multiply everything times 5. I need 5 electrons produced so that the reduction side can gain those 5 electrons. So we're going to multiply that entire side by 5. All right. So now we're ready to add these half reactions. Okay. So here we are. Let's add the half reactions together. Let's see if I can remember them. If I multiply everything by 5, I'm going to kind of write them over here. That would give me 5 of the iron +2, forming 5 iron +3, and 5 electrons. The permanganate side, that's going to go as is. We have 5 electrons, 8 hydrogens, the permanganate. We have the manganese +2 and 4 waters. So we're ready to add these 2 half reactions together. So we kind of work them separately until we get to this point where the electron transfer is the same on both sides. Now before we can really add them together, we'll cancel like terms. You should always be able to cancel the electron transfer. That should be the same. Now other things that are real common might be hydrogen and water. In this case, There is no hydrogen or water in the iron half, so the electron transfer is the only thing that's the same on both sides. So that's out. Now all we have to do is add it together. So all of the reactants, and it doesn't matter what order you list these in. 5 iron plus 2, 8 hydrogen, and the permanganate. On the product side, I should have the 5 iron, the manganese plus 2, and the 4 waters. Awesome. Okay, so before we throw a party and we say that this is all done, we should check 2 things. Number 1, all the elements should balance. 5 iron, 8 hydrogen, 1 manganese, 4 atoms of oxygen. Yep. Number 2, the charge must balance. So on the reactant side, I've got a plus 10 from the iron, plus 18 if I add the hydrogen, and a minus 1. So I should have a plus 17 on both sides. 5 times 3 is 15, plus 2 from the manganese. Yep, both sides have the charge balance and the number of atoms. Now at the very end, I may go through and add the phase symbols. Everything should be aqueous, except for the water. It would be listed as a liquid. I don't put the phase symbols in until the very end. Sometimes I honestly don't put the phase symbols back in. But if I were being proper, I would. There. 1 redox done. And that wasn't so bad, and you may have even had some fun.